Hello everyone. Hello everyone. Hello. So we will start our waiting for if someone want to join. Let's wait for a moment. So now we are going to start our video. As you know, quantum computing previously have that already developed basic logic gates as well as universal gates, and next we are going to develop some advanced gates and circuit with the help of perceptron only. Then suddenly I thought, why not to move to the advanced technology, which is a upcoming future technology. So a few days ago I have posted one community post. If you that I will that we are going to move to the next evolutionary step after AI, and that is the quantum computing. So in this video, we are going to develop some basic gates with the help of quantum computing. Today, we are not going to build on actual quantum computing. There are some simulation platforms available, and for that, don't think that this is a simulation or something. It's actually a quantum computer only. We are going to use a Qiskit software for this. Uh, with the help of Python programming and Qiskit library, you can develop any program of quantum computing. And today we are going to see how to develop basic gates. There is no need of any prior knowledge. I'm going to tell you everything while we are going. In this video, my motive is just tell you the technologies, not too much about what is this, what is that. Just bear with me so that I can help you through this. You can understand as much as you can, so that in our upcoming videos I can give you a advanced circuits as well as many logic gates, many universal gates, everything. So Let's start our today's video. So we are going to trying to run our Python program. Here already the Qiskit and all required libraries are already installed. So we are going to import whatever. First, our task is to put the which are the Qbit library. For all the files. Library. I will tell you what this library is. Library so that we can get a proper visualization, and for visualization for visualization we are going to put that plot history libraries, and we can build our basic logic gate. So before building any logic gate, let's try how the qubits work and all these things, right? So first, our task zero, you can say that the task zero. Our task zero is going to be to develop a buffer gate. I guess you all know what is a buffer. Don't know what is a let so buffer is just like this. So buffer is like this. You can assume that here is so what buffer do. Put it zero. The pass adds one. Pass as it is. So this is the logic of buffer in our traditional computer, and we are going to develop a thing in quantum computer also. So our now task is develop a buffer. Okay. So let's start developing a buffer. So to create a buffer, what we need? First need a qubit for the buffer, and for that only grab a qubit or to import or to take a qubit. Have imported a quantum library from Qiskit. So how to take any qubit? So for that, first of all, we need a variable. Let's say, and for the quantum or qubit, just a variable. Call it as you want. From one qubit, it runs perfectly. So now we draw this. How the qubit looks like. How already if you have seen the right side upper part, that qubit looks like in top or spherical form. This is the visualization for that. And now we are not going to visualize in the sphere or blob form. Visualize it in the form of the straw. Okay. Now we have just line. Here the funny thing is that by default all the qubits from the for the quantum computer came with the logic. So we have to keep in mind that all the qubits we have taken are come with the logic 0. So we can verify that also. For that we by make logic for q buffer dot, and so now you can see that here we have applied a I hope you can see my cursor by it. So this is the what we are. So we have just applied a main call function. We have just draw it. Now our next task is to check whether output, right. So we are going to visualize it with the help of this plot histogram. So for that we need a simulation variable. Then we are going to take a result. From that result we are going to extract counts and we are going to plot it. So I have already write that code. So you can that from the library we are going to backend simulation. This is exactly work like a quantum computer. Just there is a difference between the result a tiny bit, not a big difference. Then from the simulator we are going to run our quantum QC buffer qubit, and the result of this is stored in the result variable. That result counts are stored in the counts, and with the help of plot histogram we are going to plot it. Actually this is buffer output. So you can see that our output is 0. So now we have successfully implemented buffer part, right. So what we are going to do that we are going to build a NOT gate. So I guess everyone knows that NOT gate, like the input is output as 1. If the input is 1, so the work of the NOT. Now our task is to build. So how we are going to build a NOT gate in quantum computer? By default, quantum computer provides some basic gates which include gate, also known as a NOT gate. The work of the gate is to invert whatever the input is and give to the output. So we are going to build that. Let's minimize the buffer part. Start building. So I have already code for time. Like we are going to take one qubit, applying the NOT gate. So the syntax, so this is the buffer as we earlier saw. This is the syntax to apply a NOT gate. For the NOT gate quantum computing, there is just apply a dot x, which is NOT gate logic on this is the parameter 0. As you already know that in our programming language every counting is start from 0, right. So we have taken a 1 qubit. First qubit always the 0. Suppose you have something 3 qubits. apply a NOT gate second, so you are going to pass it. When you draw it, you that you got a 3, and the NOT gate is applied on the Q1 qubit, that is your number set. Now we only need a NOT, and our next part is that we are going to draw it with the help of after. We are what the major all function was here. Then a major all function measure all the output or the current point for our qubit. Suppose you apply after all function our NOT gate, then measure all function all apply. How it back to next as you can see that the output is 1, right? And in the buffer, if our output, so now we have successfully built a buffer gate as well as a NOT gate. So simple Python programming in which we are configuring a qubit for the control. It will plays a major role in future part. So now let's move forward. Now we have already built buffer gate. Now our next task is to build a next. So usually what we do, build an AND gate, then OR gate, or OR gate, then AND gate, and after that we start building NAND gate, NOR gate, that are the universal gate. But in quantum computing, already some gates are provided for us. XOR gate is provided by default with the help of a Qiskit library. So we are going to first build a XOR gate. So to build XOR gate, let's or what we can do before going for the XOR gate, let's just see our buffer gate and NOT gate quickly as only one circuit only, that we can get a basic logic where is the LSB and MSB. Basically LSB is a least significant bit and MSB is the most significant bit. That for that we need 2 qubits. And let's start getting. So now we have to all and if you see that now I have another that but want to apply NOT gate also it. So we are going to apply a NOT gate, that is, let's draw this, that NOT gate on the. Now when we are going to draw this, going to output as 10 or 0. what is going to give, because quantum qubits have a different structure that we got. So you can see that going to give the output as a 1 0 in our, that is, but so from this you can understand that Q1 or the highest qubit is the MSB, lowest qubit is LSB. So we can 5 qubit by first Android that not gate, not gate is not applied. So the output of Q0, Q1 and Q3 are going to be 1 because by default qubit input is 0, right? Let's run this function. You can see that this is the Q0, right? Q1, Q2, Q3 and then Q4. So Q4 is our most significant bit, which is this one, and by default it is producing output as 0 because its input is 0, and on Q3 we have applied a NOT gate due to which it is going to give the output as 1, right? Now take a move, then we are going to develop out by chart box at routes, and then we are going to for the XOR gate, right? Guys, let's XOR gate. You can see better. So this one, so what is that, this is whole bit target. So already you, what is the logic of the XOR gate? So for the XOR gate, when it's 1 as 1. So here the XOR gate, quantum computer, also known as a CNOT gate, which stands for XOR gate controlled NOT gate. Remember that, controlled NOT gate. So tax for this is a CX in the quantum computing Qiskit library. So let's understand logic. So as already I have told you, there is a control bit and then target bit. So when the target becomes 0 or target becomes 0, if they are same, 1, they are different, like the XOR gate. The control and target are same. Target becomes 1 1. So assume that, just forget about this part, focus on it. Assume that our Q1 bit is Q2 bit also 0. So our control bit is 0, target bit is 0. Because of this, NOT gate is going to append to 0, or assume that what next? Control bit is 0, target bit is the output like a buffer 0 0. That again 1. So control bit is 0, target bit is 1. 0 comma 1, it the output as a 1, and this is the assume that 1, this is so now you can see 1, target bit is 2 to bit. So this is last in control bit, target bit, then it's skip the output. So we can see the scene perform not on target, so is 1 and does nothing the control like that. So that is build a XOR gate Python. Let's run this. If my voice is down or in that issue, good. Part is so we are going to be for the XOR gate. Next, we need a code that I have already XOR gate. That toggle to XOR gate or to take. So, in quantum computing, XOR gate stands or controlled NOT gate, right? Because the one part is target, NOT gate, or where the control is one global. Controlled NOT gate, which is represented NOT gate. How previously see that NOT gate represented of x dot x, right? Control the NOT gate is as a dot c on whatever the qubits we pass parameter, rolled parameter, the targeted. So for this, 0 must be and q1 must be targeted. So we have applied qc not dot cx 1. So this is how we can write the syntax for the rolled NOT. And if you are focusing the that two, why I have write here comma 2, because just now computer for 0 and 1 obviously we quoting well content. Here we need two content for that. Here a line have in simple circuits, right? Okay, let's move further. Now we have now so now you can that here previously also. Okay, so that here is inputs currently. XOR gate on that, or get or out 1 0. You can see that our input are 1 1, output is 1. So how it's happen actually? So so we have applied a not 1 already for C not gate. If the controlled bit 1, that's it. How doubt or confusion that how it's working. To clear your what I'm going, let's that we can as it bits 1 Q2. Okay, I got the confusion maybe happened to your part because of mine. Let's take a 3 qubits Q0, Q1 and Q2. Now what we are going to do is that let's so currently 110, but this 0 doesn't matter. We are going to change it via let's take a 3 qubits, apply NOT gate for the Q0, Q1, and then the result of it logic. So what is going to be Q0, Q1, right? For your better understanding, just assume that Q1 and Q2 are of the same inputs or output, and after that, whatever the output is will be shown on the Q3 qubit or Q2 qubit, that is the third qubit, right? So now you can see that for the 1 1 input the output is let's for the 0 1 or 0 is 1. Okay, so now you can see that 0 is 1, 0 comma 1, 0 comma 1. So with 0 comma 1, yeah, it's wrong because I forgot to, that's why now it's 0 comma 1 1. Let's try it again. So first we'll for 0 0 put in 0. Third will be for 0 1, the output is, so now it's perfectly working. 1 1 0. I just forgot to third qubit because of this. Next we are going to build what we are going to AND gate, right? Because by default quantum computing Qiskit library provide one special purpose. That gate has a system. So if the image there is the wallet, what happened there? So Q1 is Q2 is going to toggle the input. So we are going to that by building a program. So let's start building. That let's minimize the XOR. Toffoli Gate basically both the input to Q1 are 1, then NOT gate is applied on the qubit. So for that, let's build this quite simple. I code because we can that qubits are taken. First input, the barrier is applied so that barrier is applied. It's nothing to do with the circuit. As some yes, I will tell you. Are going to make some advanced circuit where it is required. So then next is applying a CC gate, that is a Toffoli gate. So say that controlled NOT gate, like that, for our better understanding. So CC NOT gate is applied to the 0, 1, 2. So this is the first, second. These two are the controlled qubits, and third one is the targeted qubit. So these two are the controlled qubits. Third one is the targeted qubit. So we have now CCX NOT gate applied. Again, we are going to apply this barrier so that this circuitry doesn't come here or mismatch something. Now we are going to measure all the qubits for the C line, and we have just drawn it. And for the question part, so now you can see that whenever the 1 is input provided, output is 1. Let's toggle something here. Let's make it as you know now Q0 is 0, Q1 is 1, 0 1 input, and this is going to give output as a 0. As you know, MSB is the 0, and this is the Q2 is the MSB here. So this is how AND gate works. So we have currently developed multiple logic gates. First one is a buffer, second NOT gate. So this is the buffer, just passes the input as it is. And in by default in quantum computing, Qiskit library provides a qubit with the 0 logic. So this is the buffer. Second is a NOT gate, which toggles input to the output. If 0 is here, then it's 1. Third, we have developed a combined input so that we can learn how to provide a 0 and 1 to the circuitry. And using this combined input logic, we have developed a XOR gate with the help of controlled NOT gate, that is also known as a C NOT gate. So, and its syntax is a CX. So you can see that here, CX, this is the controlled NOT gate. And next we have developed a AND gate with the help of Toffoli Gate. So this is the Toffoli Gate, two controlled inputs and one target output. With the help of this, we have developed an AND gate. So if you are interested, then we can move further and develop one simple project, something like that, with the help of these gates and buffers, if you are interested. So then we can continue our stream, or we can stop. We can build just a simple gate, just like maybe half adder, full adder, something like that. We can go for the half adder because we have developed all the logic already. So half adder may be a quick application here. It's up to you if you're interested. Or maybe you can watch it later so that you can get half adder also. I planned this video as a recording video, but then I decided without doubt in, because currently in quantum computing there is not too much programming tutorials available, so I started everything with the basics. That's why I have came for the live stream. But we can, let's build a half advanced, right? We can build it quick. But if you are interested by this, you can put down your thoughts in the chat box, or if you have any doubt, then also you can put thoughts in the chat box. have decided let's build the half adder. Why not? If you watch in the future, you can definitely let's obviously build a code for this or not. How we are going half adder. Let's make it. So what we need that quantum that to input half adder. Right. Let's put 0 comma 0 0. This is the adder input output format. So let's design a circuit. So what we need. So this is up only. Let's be up whenever any one bit from or say that one bit from one bit a comma b is 1, and it's both the inputs are 1. I will just write. Okay. I will later timestamp everything so that find quickly wherever all the basic gates and all. And if you have still doubt, then to see. Hello. Wait. Hello. Okay, so there is a issue with something YouTube, and it's giving me warning. Because of this, just give me a moment to fix this issue so that I can continue my stream and the developer half adder circuit. I guess I have changed the topic name. Maybe it's changed already, right? Yeah. If my voice is too low, then let me know, please. Okay, the title is not updated. Okay, let's continue with our circuit, whatever it may be. I will then later timestamp it, and everything in the recorded video it will fix. Let's finish it before 1 hour. Why not? Okay, so quickly build a circuit. So as you can see here that, okay, maybe my screen is visible now. Yeah, visible. So we need a LSB bit. This one is the LSB, right? Take a different color. We need a LSB bit 1 only when either A or B is 1, or an MSB bit is 1 only when both A and B are 1. So just now we have developed a logic for either A or B is 1, that is the XOR gate logic, right? For the XOR gate, what happen is that giving me okay, for the XOR gate 0 1, it's 1 1 0 1. So we are going to build XOR gate here. So the input 1 2, this one is input 1, and build here an XOR gate for the adder circuit. For the NOT gate, right? We have just learned the Toffoli gate. That is the AND gate, because you can see that MSB is just ANDing of A and B. That's the circuit, but you can understand the logic. That's it. Doesn't matter. Let's quickly naming this one. You can see that this is the one our this is the Q0, this is the Q1, Qbit 2 and Qbit 3. That's it. We just need this logic, and now we are going to develop a circuit. We need a QC adder is equal to how many output we need. We just need two inputs, or let's check that. What we can we will just code, or we can add bits. We need XOR gate for the A and B, so we can provide a XOR gate here. What I am trying to do, because and that XOR gate has only one control bit and one target bit, right? So what I am going to do was this. So first I'm XOR like this. Ultimate going to give the XOR of A and B. This is the A, this is the B, and this is our Q2 qubit. So what it's going to do is that the XOR of A is done with the Q2 qubit, so the result is here now, and then XOR B to Q2 qubit and upload the result to the Q2 qubit. So this is how I have developed the logic just now. So let's apply it here. So QC adder CX, and next line again, second qubit to the third again. Now we need and CC not gate, right? So gate, so control bits are fourth. Draw the circuit. Before that we draw actually, but it's not here. Now we need to figure it. For that I just mistake error. So our circuitry is ready. You can see that Q0, Q1, Q2, Q3 are the 4 qubits. These are 4 qubits. These two are input, these two are output. So we are basically building a half adder or adder, just adder. You remember adder? Okay. So this is the XOR gate logic. So Q0 XOR Q2, whatever the result is, XOR with again Q1 and append it to the Q2. And for the NOT gate, just like we have discussed here, where it is, okay, just like we have discussed here, this is the NOT gate, which is can be applied with the help of CC NOT gate, that is a Toffoli gate, is applied to the Q3, and Q2 Q3 are measured. Finally we just need a simulation or to run this code. So quickly go to, let's copy from part. copy this one, minimize it, and then paste here. Just we need to change the some qubits. Gate is quantum adder, and this is the let's run this one. So you can see that the this is currently 1 1, right? For the 1 1, output is 1 0. That is right, because this is the MSB bit. And let's comment out any. So now current input is that you can see that 0 1. So for the 0 1, it is giving output as 0 1. For 1 0, for 1 0, it's this is the Q0 is 1, Q1 is 0. For 1 0, it is giving output again 0 1. And for the 0 0, so you can see that Q0 Q1 both are 0. Q0 0, it's going to give the output as 0 0. So this is the adder circuit. We have just developed it, and this is all about. So today we have developed a lot of gates and one adder circuit too. So we have developed a buffer, NOT gate, combine inputs, XOR gate, AND gate, and then after that we have also developed an adder too. So that's it for the today's video. If you have any doubt, then you can put it in the comment box or the chat box so that I can resolve it. No, then it's fine. You can later watch it. I am going to provide all the timestamp to the entire video so that you can easily skip any unnecessary part and you can watch whatever required. So in this today's video, we have built a basic circuitry for the quantum computer with the help of Qiskit logic. So that's it for the today's video. We will meet in the next video. I'm planning to create a video, proper video on this, so that you can understand everything without wasting any time. But still, here we have discussed a lot of important things or develop a logic live. So that's it for the today's video. We will meet in the next.